two types of mobile devices. Type 1 has both orientation sensor and an accelerometer sensor. They differ slightly, and the other type is one where the mobile device only has an accelerometer sensor. If it only has an accelerometer sensor, you cannot write games that rely on an orientation sensor. So what I've done here with the app inventor is create my own small app that actually allows you to convert the accelerometer sensor's readings into an orientation sensor reading. I have an orientation sensor app which I've opened up here. I've basically created a simple app which is designed to represent a game style app. Orientation based on accelerometer sensor. I've got a canvas here with a sprite bug, a ladybug as a sprite, facing towards the right of my screen. Now further down below that canvas, what I have is the roll, the pitch, the heading and the magnitude and the tilt of the device, the mobile device itself. The roll and the pitch are measured in degrees, and the heading is also measured in degrees. The magnitude is measured on a scale of 0 to 1, and the tilt is measured as an angle in degrees. The first reading at the top is the orientation based on an accelerometer sensor reading. The reading below that is for the roll and the pitch based on the actual orientation sensor. If your device has both orientation sensor and the accelerometer sensor, you will get both these reading on your device. However, if your device only has an accelerometer sensor, you will get 0 for the orientation sensor readings, which is your secondary reading underneath. So let's have a look at the sample code. What I've also got is an accelerometer sensor there and an orientation sensor. What I'm trying to demonstrate is the orientation calculations for an accelerometer sensor. So if your device doesn't have an orientation sensor, you can still work the orientation out based on an accelerometer. So let's have a look at the code. This is basically the code for the accelerometer sensor, and it works out the roll, the pitch, the heading, the magnitude and the tilt. Further down, I've also incorporated the orientation sensor. If your device supports one, then yeah, you will see them side by side as the readings. However, if your device doesn't support it, then you'll only see the accelerometer set readings, but converted to an orientation reading. So let's have a look at how I did this. I'm basically going to take you through a document that I found on the web, and I found very useful in working the roll and the pitch out based on an accelerometer. So let's just minimize that. What you will need to do is, I will post this orientation APK file, Android APK file, which you can install on your device and have a look at the project itself. And I will also upload the orientation sensor from accelerometer sensor PDF file, which is this file here on my desktop. I'm going to open this file up and show you what it consists of. I've actually modified this document slightly so that I've put my own comments on this document, and I've highlighted certain bits which are of interest to you in yellow. Now the whole document you can read through by yourself, but I've made distinct points where you need to understand what you should be looking at. I've clearly highlighted it in yellow, the bits that are of interest to you. What we got is the pitch and the roll estimations. Now it's quite a bit of calculations in this document. it basically is the calculations are matrix based calculations, and it sort of converts it to a canonical matrix, but it simplifies that matrix further to simple equations for the roll and the pitch. Now when you solve these equations for roll and pitch, you will get two equations for these angles. What we have is these angles are eliminating duplicate solutions as well, so that's worth reading. And what you will have is a worked example of the roll and the pitch. What I've also added here on this near equation 33 is a little note highlighted in green. That note basically says the roll is measured from 180 degrees to negative 180. That's based on the left and the right roll. 0 degrees when the screen is facing up and the device is flat. Pitch is measured from 90 degrees to negative 90 degrees. Top tilted away from you facing down, or the bottom tilted towards you facing down. 0 degrees when the screen is facing up and the device is flat. So you can find out which of these equations is the roll and the tilt based on that. It's very simple. You do not need to implement any of the matrices that you see above. What you will need to implement is one of these equations for the roll and the other for the pitch. Going further down the document, we can work out the tilt angle based on your device, mobile device. Now this, again, well, I'm just going to move this note down. What I have is, again, another equation, equation 55, highlighted as the tilt equation. Here I've also added another extra note which defines the tilt angle and how many degrees it will tilt in any direction. It basically turns out to be 90 degrees in any direction. What happens is if the screen is facing up, the angle will be 0 as long as the device is flat. However, if the screen is facing down, which means it's facing the floor, then the tilt angle would be 180 degrees. I believe the tilt is the azimuth again, which I've sort of made a little note of. However, I haven't managed to work out the north, east, south and west based on the accelerometer sensor. Maybe it's an approach that you could try yourself. What you also have is this equation here, equation 57, which is of a bit of interest to you as well. It may be used to work out the magnitude in conjunction with the tilt angle. This value, to work out the magnitude, the value will range from 0 to 1, and it is the force at which the sprite will travel in a particular heading or direction. Further down, what we'll also have is, from this document, if you read the entire document in its entirety, you will find that you can work out the heading from by looking at all the equations that are there. The heading is the direction of travel for the sprite. If the sprite is facing right and you tilt the device towards the left, what should happen in effect is your sprite needs to rotate towards the left as it's moving towards the left. And that is what I've called on my app the heading in which the sprite should be facing, and that's defined by an angle, again in degrees. Moving further down, what we have is selecting portrait or landscape mode. Well, go back to now is my project to show you clearly what I've done is basically I've set my screen orientation setting to portrait. Now that is a static portrait setting. If I did not specify this as portrait, the setting would change from portrait to landscape as you orient the device, mobile device itself. By setting it to portrait, what I've done is I've eliminated a lot of the difficulties that I would have faced in creating the app itself. But below here is a bit of code which you should be implementing if you want your device to change its orientation from portrait to landscape by itself. And that bit of code is here, highlighted in yellow here. This obviously affects the roll, the pitch, the heading and the tilt of the device itself. So if you're going to work those things out, what you will need is this little check here in your implementation. I haven't quite implemented this, but I can do if I ever need to. The reason I've left this out is to try and keep my initial project simple in order to create a portrait app, so that I do not have to change any of the equations above. Again, I've put a little note saying the same thing here, which you may want to read later on. But have a go at it yourself. Basically, this document is very crucial in creating this thing, but you will only need to implement simple equations, one or two simple equations. But try not to implement the matrices itself, because you will be overdoing it when it's not necessary. The matrices have been simplified to a couple of simple equations for roll, the pitch and the tilt. I wouldn't recommend any of you to implement the matrices itself. I'm going to upload this document for you to download, which you can download either from my website or from YouTube channel. I will also demonstrate now the orientation app on an Android device, which you will get to see as I tilt it based on the accelerometer sensor. What you will notice is my device doesn't contain an orientation sensor, and this is why I've created this app. What I have here is my mobile phone, and on it I have just put on and installed my orientation demo app APK file. What I'm going to do is just click on that file and run the demo. Here what we got is the bug moving in the direction that I'm expecting it to move. Just going to demo it from a distance for a bit. So that's the middle of the screen. It's moving where I tilt left, right, left, up, down, up, down. As you can see, the bug is actually facing, is traveling in the direction that it's supposed to, and it's actually facing that direction as well. You can change its direction. Right, let's pay a bit more attention to what we've got on here in terms of the roll, the pitch, the heading and the magnitude. What you'll notice is when it's virtually flat, it's 0 degrees roll, 0 degrees pitch, near or thereabouts. It's basically dependent on the way I hold it. The magnitude is 0 roughly, as it's not moving and it's flat. The tilt again is 0 degrees. Now what you'll get, the roll, if I roll, put the left hand side down, which means the bug drops to the left, what you'll notice is the further I take it, the further it goes, but at 90 degrees with the ground, it should be, the roll should be 90 degrees. Similarly, towards the right,
the roll should be negative 90 degrees, as it's 90 degrees to the ground. Then the pitch, as it's tilted away from you, which is that 90 degrees to the ground, the pitch should also reach approximately 90 degrees. It's a bit difficult to capture that, but I'm just going to try and give you an idea as to 90 degrees there. And when I change the pitch down towards me, there it is, negative 90 degrees, the pitch, and the bug is facing down, as you can see. And the heading again changes depending on which direction he's going to travel, and that heading is again in degrees. The maximum tilt here we see in any direction would be 90 degrees. If you see that, the tilt, 90 degrees there, 90 degrees there, 90 degrees there. The pitch, the roll should be as far as 180 degrees. There is negative 180. I think I made a mistake earlier, but as it's pointing to the ground, the roll should be negative 180, and towards the left it should be 180 degrees. There it is, the roll is 180 degrees. As it's pointing, as it's 90 degrees to the ground, it should be 180 degrees in terms of roll. So if you can see all the information, as I move the phone around, the bug seems to move in the direction that I tilt the phone, as well as the heading and everything is being updated as it's as I tilt my device. What you'll also notice is the second value under the roll, the pitch, the heading and the magnitude is all set to 0. What this suggests is that my device does not have an orientation sensor, and this is purely working off the accelerometer sensor. So the values that are being changed are based purely on the accelerometer sensor, and it's working purely off an accelerometer sensor. The orientation sensor value is supposed to be below the roll and pitch value. Currently they're displayed as 0. But have a look at this app yourself. If you manage to write it, or if you don't, install this app on your device and see if it works based on the fact that you've only got an accelerometer. What you'll see is the bug moving in the direction that it's supposed to move based on the tilt and the pitch and the roll. So have a look at the file, download the file from the download link, and basically try it yourself.